the MKU 4363 mechanism design. So today is our last class for this semester. Will be a revision for your final exam. So let me share my screen and let's start talking about the final exam. Okay, I hope you can see my screen now. And let's focus on this one. So the topics that will be in the final exam will cover screw, and usually screw will be coupled with some linkage. And then there'll be a question on robot kinematics, which will focus on the inverse kinematics part. And then planetary gear. Planetary gear, there are two ways to solve them. So I will show you or review on the both two methods. And then there is gear analysis, chain drive design, as well as slider crank. So those are some of the topics. Some optional, some part of the compulsory section. So maybe we have seen this kind of problem for the screw. So power screw is usually not a standalone, so it'll be coupled with something else, usually linkage. So here we have the scissors lift mechanism, and it is being actuated or powered by a screw, hand crank screw. And crank screw. So you can see this the crank on this part. So it is partially solved, or if you refer back to our notes on this topic, you'll see this solution as well as the question. Okay, so how many ways can we control this thing? Okay, so it depends on how many input that we can control. In this case, it seems that this is the only input that we have. So this system is basically a single degree of freedom system. So if you calculate or analyze the degrees of freedom, the mobility, you should be getting one DOF, 1 degree of freedom. Okay, so that is the situation for this problem. And I think we have seen this thing, this the initial part in that position when this base is 18 inches, whereas after some cranking, the base shrinks to 16.75, and that causes the height to increase from 15.87 to 17.19. So in this situation, we see that this thing has a slider up there, and that is shown by the pin and slot. Okay, so how about we want to show the work on how we can get the 1 degree of freedom system. How do we do that? Okay, so maybe have to go to use pen. So in this case, I draw this thing. So I can draw this thing. So it has here like that, and here we have this thing, a pin or revolute joint, then another jumper for the second part, and then this part needs to go on the way. Yeah. This one is connected to the nut. So this is the nut. Yeah, this nut is not ordinary. It is constrained to work in a certain ways, in a certain way. That such a way that it is going to be connected to the screw, as well as it is constrained by not being able to rotate, and meaning it also slides on the ground. So in this case, screw will be when you turn the crank, the screw will turn. The screw will turn, but the nut should not be turning. It will just slide to the left or to the right. Ke kanan, ke kiri, something like that, if you will. And this power mount, this screw is not going to be floating in the air. It is being supported by this power mount bearings. So supported by bearings. Okay, so this is bearing. I have one bearing there and another bearing here. Another bearing here. Another bearing there. All right, and let's do the ground. And maybe we can also do the hand crank like that. Can add that. All right, this is not done yet. At the end of this over here, you have the pin. And it is moving in a slot. Something like that. And then this part will continue here, and it is connected like that. Okay, so this is the kinematic diagram, not really beautiful, but I guess you get the idea. Then we can go on and label the ground to be number 1, numero uno, number 2 here, this part is the whole thing. The whole thing up to here is number 3. Number 4. And this one, the nut, is number 5. This bearing, or the screw person, this screw is number 6. Then we have the 2 more bearings. So that is number 7, and this one is number 8. Okay, well, once you get that done out of the way, so here meaning our end is 8. I hope you get that part. And later we need to find what our J1 is. And also in this case, have a J2. Okay. For J's is the joints. Joints. So we have J1. J1 is marked by lowercase letters. So we have A here, A, so B, C, and this one will be a J2. This one between the nut and the screw will also be a J2. Okay, for J1 we have A, B, C. This one over here will be a D. D, and between the nut and the ground, E. There's also sliding, so that is J1. And then what else? Then between the screw and the screw and the bearing over here. So here we have one is supporting it this way. Another one that will constrain from going from the screw to go to the right. So we have another one that will push it this way, constrain that way. Same over here. The screw is supported in this way, and also not allowing it to come off to the left. So pushing it this way, constrain it this that way. So that will be E, E, F, A, B, C, D, E, F, G. This one will be G, and this one will be this one will be H. Okay. So let's count A, B, C, D, E, F, G, H, I. So that one will be a 9. And we have 2 J2s, one for the pin in slot, another one for the screw between the nut and the screw. So that will be a 2. So if we do the calculation for the mobility, it minus 1 minus 2 times 9 minus 2. So this one will give you what? 21 minus 18 and minus 82. So that, ladies and gentlemen, will give you Uno T O F. Okay, capiche? Do you understand? I hope you do. I really hope you do. How do I get back to? Okay, let's get back to this. Okay, the next problem will be the planetary gear. Planetary gear is something like this. So this one is a problem that you can find in Mishka's book, textbook, and here you start off by creating the table. So there are two ways to do this. One is the table way method, and then the other one will be the equation method. So in this situation, so why is it so big? So maybe maybe this is too big. I don't know what's going on here. I guess can do that. Will be this, I guess. Okay, and then bring it this way. Mm-hmm. Hold on. Mm-hmm. Okay, that is better. And yeah, okay, let's try to go back here. So this is from the method I guess presented in the class. We either give for the first step, either give a plus or minus. In this case, a plus. So everything, all the gears and also the arm or carrier will be given a 1 plus 1. And then we see in the second one, arm will be lock the arm, so meaning here will be 0, and for the third step, this one will be 1. So it's a summation, and from the problem it says that the sun is fixed, meaning in the end the sun will have a total of 0, which means that in order from +1 to get 0, the second step the sun will have a -1. So that is the initial part. Then for the other cells, you can either do the calculation there, or you can just label them by letters and do the calculation outside. So actually, because we are having limited space, it's better actually to do the calculation outside. All right, here actually we want to find if for gear label 3, which is the first planet. So meaning here basically you want to find omega-3 in the second step. So it's not the ultimate omega-3, but omega-3 for the second step, and that is going to be related to this one, because this is another non-zero. This will be the input for the second step. So whichever gear that has a -1 or +1 value, that will be the input. So in this case, omega-3 over omega-1 will have this kind of relationship, which is N1 over N3. We can then solve for omega-3 using this ratio. And then from that ratio, you can solve and get 0.4761 positive. And then you can find, you add that with the +1, and then you get 1.4761 for the total. And you pretty much do the same thing for other gears. Yeah, this gear, C and also E. C and E. E is the ring gear. And Y4 is equal to 5 because 4 and 5 share the same shaft. So they will have the same omega, angular velocity. Okay, so you can try to follow this thing. And in the end, in the reality, what is the real input is not this first one. What is the real input here? Determine the rotational members of this gear when the input shaft rotates. Input shaft rotates at 680 RPM clockwise. So in the carrier link, so carrier, the arm, is the input. This arm number 2 is rotating 680 clockwise. Clockwise is a negative. That is the situation. So meaning you have to find the omega-3 related to omega-2. So that's why you get this one from the table. So this is 1.471 and divide by this +1. +1, and then you get this number, so on and so forth. Okay, alternatively, if you use the formula method, you have to be careful. You have to decide, I guess, this is the last gear, and so whichever last or first, you have to decide lah, whether you want to go from the sun to the ring or ring to the sun. So that will affect your setup here. In this case, I'll go from the sun to the this one because you want to find less is actually it goes both ways lah. Even if you want to say the first one is and so even if you say you flip this, so that one will be last one will be omega 3 minus omega 2. So this one will be omega. First one is the first one is 1 minus omega 2. So in this situation, I guess N1 will be on the top, N1, and then omega 3, N2, N3 will be on the bottom. And between N1 and N3 is external gears, so they will have opposite direction. Okay, so I guess if you solve this thing, you will still get this answer. Okay. Okay, just be consistent whether you want to go from the tail to the first one. So you have to decide which one is the last, which one is the first. Yeah, the answer should be the same thing. All right. Here's something that I tried on using this is something I tried using SolidWorks, and angular speed is this one 536 for the I guess the arm, and then we get 32 gear 6. Gear 6 is what the big one, ring 3217. 3217. So I guess that might be a different example. Yes, different example. Anywho, we have another example here. Yeah, so you can look at the solution here, and this is the solution using table method, and this is the solution using formula method. So I guess they should agree. So omega A is 180 CCW positive. Omega B is negative 90. So this one will have the same conclusion. Okay, the next topic will be the inverse kinematics. So I guess we have seen this before. Here, the menthol or the pulp is all the way up at this position, and the orientation is like this, which is negative 90 lah. You measure at the base here. So if you measure at the base here, this orientation will be a negative 90 degrees. Negative 90 degrees. And meaning the third arm here should be pointing up lah. So this one should be the gripper, should be something like this lah. Will be pointing like that. And what do we call that angle? What do we call that angle? So this angle will be 90 degrees positive. Okay, so that angle is a positive 90 degrees. So this we are talking about this one. All right. So definitely we have to use this solution. We have to calculate A, B, and C. Then depending on whether our A is negative or positive, so you can do this. And this part you should always do the negative first, minus. In this case, because A is negative, so this we have a plus 180, and then we have theta 2. Just use the theta 1 inside here and got theta 2 of negative 43.94. And then we can calculate theta 3 lah, theta 3. Then just plug in those information, those solution into this verification and see whether we can get the big X or big Y. Okay. And this is another screw problem. So screw. So you got to look at this thing. So this diameter of the screw here. If I can. So this is diameter of the screw. That's the diameter. Major diameter, but this one is that information is on this thing. Then pix per inch. Okay, 10 pix per inch. We're talking about the pix for the screw, either pix or the belly. Okay, from those information, you can get what the P is. Pitch. What is the pitch? P, pitch P, small p, will be 1/10 inches. Okay. All right, then you can do this thing, this relationship, pretty much the trigonometry, so, or geometry, and you can solve that. Then the topic will be chain drive. So basically, you have to solve for this one is a design problem. Here we are given the center to center distance, which is designed to be 37 inches. Okay, so there are a few other information like 600 RPM for the motor, so that is connected to here, and so on. $600, and you want to get it down to 250. So over here is 250. All right, from that information, you can find 1 horsepower being delivered at 600. So meaning you are in this region. 35 is the chain number. And then you can find the velocity ratio as well as the you can find the diameter. And then yeah, a lot of stuff can be found. So since the chain number is 35, you can find from here. So you can try from 4 to 45, and then another one is 96. Okay, so our velocity ratio is 2.4. Okay, you can do some, you can try to follow this information and this solution and see in the end we have we can calculate the VC, chain velocity. Then we can have diameters that can be suggested from this information. Diameter should be around 5.6. Okay, 5.6. So if we already know this thing, we can manipulate this equation from here. You get something like this, and we can find 5.6 is equivalent to something that is 40 teeth. So we have 40 teeth in chain number 35. So 40 teeth some is within this range. Okay, so that is available, and to get 2.4, meaning our N2 needs to be 96. So we have a 96 there. So then the next one is to plug in this information. We want to find a C, which is between 30 pitch to 50 pitch, and meaning since we want 37, so that is actually out of this range, out of that range, but it's okay. So we can put 37 there. Here, and this will get us the number of links is 238. And we plug in into this equation just to check. So 238 is over here. Plug in the values 96 and 40. That gives you the velocity ratio, and then we get something that is very close to 37 inches. Okay, and then we have a train analysis problem. It would be something recognizing something like this, ordinary gear trains, do this kind of calculation. And we have compound gear trains as well as reverted gear trains, and then we have planetary gears and whatnot. So this is one example. There is no answer here. Maybe I have showed that in class. So here we want to find what is the omega out in gear number 5. And this is how to recognize the direction for this kind of problem. So we need to find out this is one that is a right hand worm, and if it turns this way, so you wrap your 4 fingers over here like this on the right hand, and then the direction of shown by your thumb will be direction that this one will go if it goes if it is not restrained. So since it is restrained, so that it can just rotate about its axis, so the mesh member will go in the opposite direction. So 2 will rotate, a point in 2 will go in that direction, causing counterclockwise direction. All right, and then slider crank. You can have this kind of problem. So maybe you guys might have a different way. So I would suggest you either use the vector method or the formula method. So the formula will be given, and you need to know how to use the formula. Same here, if you have this kind of problem, you have this thing connected to a slider, okay, and you can find what the position of point P is relative to point O, and then maybe you can also be using different methods in order to solve for that, for the velocity of point P. Okay, so I guess that'll be it in terms of what to revise. So I hope you will not be panicked, and will try your best in order to solve the problem and be on top of the game. Don't be afraid, but if you have any question, feel free to contact me personally, and I will be glad to address your concerns and questions With that, thank you very much. I will share this presentation very soon. I hope you can learn from it in order to prepare for the final exam. Assalamualaikum. Have a good one. Bye-bye.